Hello and welcome to this lecture. So let's look at a few more interesting eigenvectors and eigenvalues. These are special cases. So here are cases where looking at the matrix, you may be able to figure out some eigenvectors. Okay, so for that we need a notation. I'll use this all ones vector. This is the all ones vector, and that I will denote as 1 subscript n. When I say 1 subscript n, I mean all ones vector. And then this EI is standard notations, canonical basis, ith coordinate alone is 1, everything else is 0, EI is the canonical vector. So we are going to ask, when will a matrix have 1n, all ones as an eigenvector, and when will the matrix have EI as an eigenvector? Okay, so this is a nice question. Sometimes you can just view the matrix and pick up these things quite easily. Okay, so here is A which is an n cross n matrix. So let's ask, when is 1n an eigenvector of A? If it's an eigenvector, then what should happen? A times 1n, A times 1 on the right, okay, all ones on the right should be lambda times 1. Okay, so what do you have here? On the left hand side, you have sum of the rows of A. Okay, sum of row sums of A. Okay, I think that's what's correct. So A times 1, hopefully you see when A and all ones you multiply, every row gets summed. You will get a vector where every for first entry is the first row sum, second entry is the second row sum, so on. Every row gets summed and you get that as the column. Okay, and that needs to be equal to lambda. RHS is a constant vector. Okay, so what does that mean? When will you have this possibility? When will A times 1n be a constant? When all row sums are the same constant value. So if you have a matrix A and if you inspect it and see that all the row sums are the same, exact same value, then you have an eigenvalue which is equal to that row sum, and the eigenvector is the all ones vector. Okay, so all ones vector, when you multiply that, you will get the same constant row sum in the vector, and that you can pull out and make it your eigenvalue. Okay, so this is a very nice vector. So this all ones, very nice fact, you can use it quite often. When the row sums are constant in a matrix, then all ones becomes an eigenvector with the eigenvalue equal to that value of the row sum. Okay, so this is an important thing to use. This is used quite a bit, and in some probability applications these things are used. Okay, so what about E? When will you have a canonical basis as an eigenvector of A? Notice what should happen here. A times EI should be equal to lambda times EI, okay, which means the LHS is the ith column of A. Okay, what is RHS? It's lambda times the ith column of A. So the ith column of A should be proportional to EI, right? So only the ith entry in the ith column of A should be non-zero. Everything else should be 0. Okay, so ith column of A has to be constant times AI. So if you see that the first column is 1 followed by zeros, or some constant followed by zeros, or say the ith column is only the ith value is non-zero, everything else is 0, then EI becomes the eigenvalue, and that whatever that constant is will become the eigenvalue, and EI becomes the eigenvector. Okay, these things are sort of easy to identify. You can quickly see that when you will have the all ones vector as an eigenvector and EI, the canonical basis, as an eigenvector. Okay, so this is one special case. Sometimes in computations this is useful. Okay, now let's move towards looking at complex eigenvalues, eigenvectors. I didn't give too many examples involving complex numbers, so let's do that, because eigenvalues can be complex. Okay, so we should see that. So here is a 2 cross 2 real matrix. Okay, and if you do eigenvalue computation, you're going to do A minus lambda I, the usual method, and then you're going to find determinant A minus lambda I. You'll get 1 minus lambda whole squared minus of minus 1. So you get 2 minus 2 lambda plus lambda squared, and lo and behold, you got complex eigenvalues. The eigenvalues are 1 minus I, 1 plus I. So in fact, this matrix is sort of like a rotation. If you actually see it, it will be a scaled rotation. And rotation matrices cannot have real eigenvectors, right? Because they are rotating. Any vector you have, it will rotate. It will never be invariant, right? So I think I mentioned this example maybe when we looked at R2. So any rotation will not have. So, but in the complex world, of course, you have eigenvalues. So when you go to complex world, it becomes a more complicated space. So you can have eigenvalues, and these eigenvalues are complex here. You can see complex, but complex conjugate. Okay. So whenever you have a real matrix, if you have complex eigenvalues, they will occur as complex conjugate pair. It has to be true, right? Because the characteristic equation will be real. It's a real polynomial. Real polynomial, if it has a complex root, the conjugate will also be a root. So this is how this will work out. Okay, with respect to finding eigenvectors, the procedure is exactly the same. So, let us look at lambda equals 1 minus I. There's nothing different to do. Complex field and real field are pretty much the same. You have to just do complex operations, and then that elimination, finding null space, everything is exactly the same. So, null space of A minus 1 minus I into I, okay, capital I. There nothing changes. So, you have to subtract 1 minus I from the diagonal and then do it. If you do that, you will get the same thing. So, you get I on the diagonal and 1 minus 1 here, multiplied by x1 x2 equals 0. You solve this, you find the solutions, you get the null space. Okay. So, how do you solve? You do elimination. In fact, sometimes it is a bit tricky to observe. See, in fact, the second column here is a multiple of the first column. You multiply both sides by minus I, okay. You multiply the first column by minus I, right. So, you will get minus I squared, which is 1. Minus 1 into minus I is 1. So, it's like these two are multiples of each other. It is a bit harder to see, but if you notice that, you will quickly get to the answer. But otherwise, you can do elimination. You can just do elimination just by before. You will get a 0 0 here. You will get I1. So, your x2 becomes a free variable. You pick it as 1. Then x1 has to be I by solving. So, you get an eigenvalue V1 is I1. I mentioned this I times 1. If you multiply I by I here, and then this will go minus 1. So, you get I1. That's the thing. You can check very quickly that A times V1 is actually 1 minus I into V1. Again, you can check this is a little bit involved. So, the computation can be a bit tricky with complex numbers if you are doing it by hand, if you are not used to these calculations, suddenly look a little strange, but the procedure is exactly the same as for the real case. Okay. So, you can do again for 1 plus I am not going into detail, they write down the same sort of steps and you will get the vector V2 as minus I1. Okay. So, what is the moral of the story here? You can have a real matrix for which the eigenvalues are complex and the eigenvectors are also complex. Okay, so, complex can enter in different ways, but if you have a real number matrix, then the eigenvalues will occur in complex conjugate pair. Okay, so, that is a very important thing. Okay. So, you can see not only the eigenvalues, so maybe I should just show you one more little result here which is not mentioned here. So, if you have AV equals lambda V, okay, and you can take suppose A is real, you can take conjugate on both sides. So, you will get conjugate equals lambda conjugate V conjugate. But notice here this A bar and A are the same, right, they are equal, A is real. So, this means A V bar equals lambda bar V. So, if lambda is complex, lambda bar is not equal to lambda and this is also complex eigenvalue. Lambda bar is also a complex eigenvalue. Not only that, if V was an eigenvector, V bar will be an eigenvector. Okay. So, for the complex case, you can do this very easily. So, you notice that also happens here, right. So, if you do 1 minus I, it is enough if you do this you do not have to do, that is what I am trying to say, right. If you do for 1 minus I, if you just conjugate it, you get 1 plus I, and you can conjugate I1, you will get minus I1, and this you can do only when A is real, okay. If A is real, you can do it. If A is not real, do not do it, but then you will go wrong, right. A also will get conjugated, the matrix changes. So, that goes, if A is real, then this will work out. Okay, so, this is something that can happen with even 2 by 2 real matrices. Of course, there are 2 by 2 real matrices for which everything is real and then there is no problem. Okay, so here is a 2 by 2 complex matrix. So, the matrix itself is complex. Okay, I have put 1 I minus I1. I have chosen this a bit carefully. So, if you do A minus lambda I and then you take determinant, lo and behold, you get lambda into lambda minus 2. So, your eigenvalues are real. Okay, so notice what has happened here. I have got a complex matrix with complex entries, but my eigenvalues are real. Okay, so this can also happen. So, this happened in this particular case and it can happen in more general cases. The eigenvalues of a complex matrix can be real. Okay, so that is true. But it does not matter whether they are real or complex, you can always solve for the null space. So, you do for lambda equals 0, you subtract and you get this, you get minus I1, and then for lambda equals 2, you do this, you get V2 is I1. Okay. But here you can't do the conjugacy and all that. I mean, it does end up being conjugate, but that's just for some other reason, not for the obvious reason of taking conjugate. Because if we take conjugate element wise, then the matrix A will change. It will go 1 minus I1, and then you will do something else there. Okay. So, hopefully you see this. This is another illustration of a case where the matrix was complex, the eigenvalues were real, and the eigenvectors were also complex. So, this is a case that can also happen. Okay. Can you have a complex matrix for which the eigenvectors are real Yes, it's possible also. So here is an example of that. You've got a complex matrix 1 I1, and then if you do the calculation, you will get the eigenvalues as 1 minus I, 1 plus I, and if you do the calculation, you will get the eigenvectors possibly as minus 1, 1 and 1, 1. Okay, so this is sort of closely related to so many other things we saw, but then you see minus 1, 1 is one eigenvector, 1, 1 is another eigenvector. So the eigenvectors are real. Okay, the matrix is complex, eigenvalues are complex. Okay, this can also happen in some cases. Okay, so it's important to keep in mind that complex values can show up in various different ways in eigenvalues and eigenvector calculation. Okay, so let's stop here and pick up with the next topic in the next lecture. Thank you very much.